Hello there. Hello there. Thank you for visiting my YouTube channel. Today I'll be presenting on my statistical machine learning project. And without much ado, I'll just want us to jump into it. So basically, we've got two tasks here. The first task is a regression task, and the second task is a classification task. So for the regression task, here we just loaded our data set, and then we can see that the y variable is continuous, right? It's a numerical and continuous data. Hence we have the case whereby the data is we hence we have a regression task, as simple as that. So the size of this data is simply 225, and we can see the dimensionality of the data is just one, right, which is the predictors. We just have one predictor. So formulating the data, we have we just have, as I mentioned, we have a numeric predictor, just one of it, and then the response variable, the y. So this is our scatter plot. We can see in a nonlinear relationship existing between x and y. Hence, we need to model this with the polynomial. We can clearly see a polynomial behavior. You can see polynomial behavior there, a polynomial relationship, or sort of an oscillatory relationship. So we jump right into a theoretical framework. So the first thing is to assign an appropriate function space. All right, and following Weierstrass approximation theorem, we can simply use a polynomial for this course. So the loss function is simply the squared difference between the predictors and the response variable and the predicted value. So also here we have that the theoretical risk is simply the expectation of the loss, whereas Bayes learning machine seeks to minimize the expected squared loss. That's to see the risk, the risk function. The empirical risk, uh, as it sounds, is simply an approximation of the theoretical risk. So we'll go the ordinary least squares estimator. Ordinary least squares estimator simply minimizes empirical risk. Okay, so without much ado, we'll just jump right into our plots. So cross validation, carry out the cross validation, and then over here we can see that the empirical risk, as theoretically it keeps going down, and we can't trust it enough. So we have to carry out a cross validation, and we can see that the best spot, that's the sweet spot, is at p equals 10. Okay, so so over here we can see the simple model, which is the brown line, and then we can see the complex model. But the best model, the optimal model, is simply formed with the green line, the green curve rather. So this box plot is a box plot of which still indicates the optimal model, is the box plot of our test errors. So we carry out an ANOVA test here. And from this ANOVA test, we can see this p-value. P-value is very, very close to zero, which of course is less than 0.05, which is uh, which is which indicates that a model performs. We have at least one model that performs the best. So we just go right into the confidence interval, and the confidence bound and the predicted bound. We can see the confidence bound simply gives us the confidence bound gives us, it gives us a room for uncertainty. It gives us a room for uncertainty. We can't always be sure that the blue line will serve as an absolute predictor. So, okay, so we jump right into the classification. The classification. For the classification, we have spam and non-spam. So we're trying to classify into spam. We have a very, very large input space with dimensionality of 57. This is really difficult for some learning algorithms, and because of this they can run into what is referred to as the course of dimensionality. And over here we can see the types of inputs, and also we just go right into our ROC curve. Our ROC curve here shows that out of the learning models, LDA and FLD overlap. That's to say that they are the best. We can see they are very close to one. They are very close to one, and they will be referred to them as the best models. And the next following is QDA, and naive Bayes is performing the least in this case. And yes, the reason why we have this case is basically because naive Bayes assumes independence, and whereas and also QDE doesn't perform very well with multicollinear data. Okay, and then here this gives us our error. The stochastic holdout gives us our error, and then lastly we can see plotting those test errors. We can see of course FLD and LD perform the best, and then QDA follow, and naive Bayes. So with this, I just want to appreciate you for watching this video, and have a nice day.